Thanks. I don't know about you, but I need to recall what we did yesterday. So E is an elliptic curve. As always, defined over the rational numbers. N of E is the conductor. P is going to be a prime. As we move on, P is going to be odd. Sorry, John. And for the most part, P, I'm going to simplify matters by taking, at least for these lectures, P a prime of good reduction and even ordinary reduction. And let's recall what this means. So if we take T to be the Tate module of the elliptic curve, then this meant that there was a filtration on the Tate module. The most important part is the submodule, and this was a filtration for the local Gawa action. So the Gawa action of the Gawa group at P, so which I can identify with the absolute Gawa group of QP. This QP filtration. V was the p-adic Tate module, so I've extended the coefficients in QP, and W was V mod T, if you like, which is T, just T tensor QP mod ZP, which is identified with the P divisible group. And to add a little twist into things, I'm going to also consider a character, chi, of the Gawa group of Q, so it's going to be a Gawa character. Later we may want to consider characters over other fields. I'm going to take for the moment for this character to have finite order, so really it takes values in the roots of unity, which I can sort of embed in any algebraic closure. I'm going to think of this as in QP bar. This is a finite order character. So it's the Gawa representation associated to some Dirichlet character, like global class field theory. It's, as I said, its values are in the roots of unity of some order. So it'll generate a finite extension, possibly of QP, maybe, and that'll have a ring of integers, which I'm actually going to change a little bit. I'll write it O sub chi. This is going to be the ring of integers of the finite extension of QP generated by the values of chi. So I'll say generated by chi, if you like. So, and so then we'll have some notation like T of chi, the twist of T by chi. If chi is not valued in ZP, then I have to extend scalars to make the Gawa action, make chi act on something. So this is T tensored over ZP with O chi, and now the Gawa action is through the action rho on a rho of EP on the Tate module, and then twisted by chi. So I'm acting, the Gawa group of Q is acting as by rho of EP on T, and by the character chi on O chi. So that's what this notation means, T of chi, the twist. And similarly, we'll have V of chi and W of chi, defined in exactly the same way. Okay, this is giving me a GQ action. Okay, so that gives us some framework. Well, we'll put that there for the moment. So then we had a Selmer group. I talked about it mostly for the case of the trivial character chi, but everything goes through for the twists. So we'll have sort of the Selmer group for E, twisted by chi, as the collection of classes C in H1Q, coefficients now, in the twist of the P divisible group, with the subject to the condition that the restriction of these classes vanish for all L different from P and at the Archimedean place. And then that the restriction at P of the class lands in a particular subspace, and the subspace is the subspace determined by T plus. So I'm going to decorate T chi, V chi, W chi with a plus to mean replace T with T plus in the definitions. It should be clear. That'll give a local Galois module. So I want this to belong to the image. So if we have H1 QP of T plus chi, we can, and again, okay, well, the map, that induces a map into H1 QP of T of chi. Actually, this should be W, so, sorry, W chi, W chi. Now you have no idea what I wrote. And so you have the image of that, and we take the maximal divisible subgroup there. You can also have rewritten this as the maximal divisible part of the kernel of H1Q of W of chi projecting to H1Q of W minus of chi. So exactly the same thing. So maybe we can even write that. So that would be the same as the kernel of H. There, you can see what I'm writing. So there. And the induced map to W minus of chi. We take the divisible subgroup of the kernel. So that's, well, same as saying it belongs to that. So those are our Selma groups. This is a slight generalization of the Selma group, the standard Selma group for the elliptic curve, and this was part of my point of sort of emphasizing that the Selma group for the elliptic curve could be defined solely in terms of the p-divisible group, and so then we can start to define these things more generally. So this gives me a nice actual family of Selma groups, and one of the things I said, maybe I'll do this, just, okay, it's probably yesterday was that experience at least has shown us that it's good to study things in families. And the family I'm thinking of here is the family of twists by these characters. And I'm going to even restrict which characters that we look at. And so following some of the earlier talks, we know we have Q infinity over Q, the a cyclotomic ZP extension. So it has a Galois group gamma. And once we pick a topological generator, that gives us an isomorphism with ZP, and it also allows us to identify the Iwasawa algebra of gamma, the completed group ring, with the power series ring in one variable. And so I'm going to have a sort of a canonical character, which I'll denote by capital psi, which is just the projection of the Galois group of Q onto the Galois group of this cyclotomic extension. And I can think of that as actually taking values in lambda. So that's a lambda valued character. That's just another way of writing some of the characters we saw this morning. All right, so I'll probably use this star to mean Pontryagin dual. So this is the continuous homomorphisms, group homomorphisms from this compact group lambda into QP mod ZP. So this is a big discrete, divisible discrete group. I give it a lambda structure in the obvious way, just by the action on lambda itself. But I'm going to give it a Galois structure using that action of lambda through the character psi. Actually, I'm going to allow GQ. I hope the cricket was aware of that little action there. All right, so we're going to, I'm going to have the Galois group Q act on the Pontryagin dual of lambda through the inverse, actually, of this canonical character. We already saw that in Romyar's treatment of the main conjecture, the proof of the main conjecture. There's sort of a reason for doing this convention, but I'm just going to make it, and we're going to have to live with it. And so then I'm going to construct a large discrete module from the Tate module and this lambda star. So I'm going to take M to be T tensor of ZP of lambda star, and so now we're going to have an action of the Galois group on there. So we'll have, again, the usual action on the Tate module, and then we have our twist by this sort of canonical character. It may not become evident why I'm using this inverse until maybe tomorrow when we start to look at things in relation to main conjectures. All right, so that's not so bad, although maybe we'll do it that way. I don't. Yeah, I don't want the second page. So one of the things, why have I defined this module M? Actually, this module M can be thought of as packaging together all of these W chi's. We certainly have an action of, at least for the chi's that factor through gamma. So if we take chi actually to be a character of gamma, again of finite order, I can sort of abuse notation and also think of this as a Galois character by composition with this canonical character, psi, and I can sort of ask what's the sort of the chi isotypical part of M, if you like. But again, this character chi might take values in a slightly larger ring than just ZP, and so in fact, generally it will. And so we can look at M, and we can extend scalars to O chi, and then we still have a Galois action on there. And then we can look at the sub-module where gamma, so gamma is supposed to be a topological generator of capital gamma. I can't write upsilons, so that's a topological generator. And since it's a procyclic group, I only have to tell you where the topological generator is acting. And so I look where that's acting through, say, chi of gamma. Now, gamma is acting as multiplication by gamma inverse because of this inverse on the canonical character. Again, I'm abusing notation a little bit and thinking of gamma as an element of GQ. So I can take any lift of it to GQ, if you like. So what is this? So this turns out to be naturally just W chi. How do you, maybe instructive to see how to see that. So if we want to think of M is this T tensor ZP of lambda star, but I can think of that then as the Homs from lambda into T tensor QP mod ZP. Continuous homomorphisms. There's my W already. And then when we tensor with O chi, we have M tensor with O chi, as we can think of those the Homs, the continuous homomorphisms lambda tensor O chi, and maybe we can even make the O chi linear homomorphisms into T tensor O chi tensor QP mod ZP. Okay, well, and then when I take the gamma minus chi of gamma part of this, by duality that's modding out by gamma minus chi of gamma here, and that becomes what happens when I mod out by that. That becomes O chi with the chi inverse action because of how psi, I mean, well, actually, yeah. And then you take the Homs into that. So that's probably confused you more than you need to. Exercise. Maybe I should put that one underneath too. Takeaway. The M is packaging together all of these sort of discrete modules, this whole family of twists of the p-divisible group by finite order characters. And so what we can imagine doing is then taking some large Selmer group for this module M and maybe see it as packaging together the Selmer groups for all of these twists. That's a perspective on Iwasawa theory, at least on the algebraic side of Iwasawa theory, that you can find in many of the papers of Ralph Greenberg, which is where I learned this kind of perspective. I don't know if he introduced it, but he certainly developed it. Right, so now we're going to do the Iwasawa Selmer group. So this is going to be the Selmer group of which I might in my notes I think is something like S of E over Q infinity. And instead of taking or defining it as sort of a directed limit of Selmer groups of the elliptic curve defined over larger and larger fields, I'm going to define it as a cohomology group over Q, but with coefficients in this very large discrete Galois module M. So it's going to belong to, elements are going to be in this HQ of M. So we're going to take classes inside here, and then they're going to have to satisfy certain conditions. And you can already guess what the conditions will be. So the restriction at a prime L different from P is, well, actually, I can define it in two different ways that turn out to be equivalent. I can make it just to be equal to 0, or I could say just that it's, in this case, unramified. And this might be the one that you see more often. But it turns out, well, that's going to be equivalent here. That's for L not equal to P. And for L equals to P, you already know what it's going to be, that the restriction to P at C essentially belongs to the image of some map. So in this case, it's going to be H1. And now, maybe I'll define it in terms of the kernel. So it's in the kernel of the map from H1. Of course, when we restrict, it lands in QP of M, and then we'll project to the minus part. So that's just the T minus tensor lambda star. But I'm going to ask not just in QP, but I'll say unramified. So it vanishes when we restrict to the inertia group. So in the kernel of that. So essentially, the reason that these conditions would be the same is that, as has been mentioned before, in this particular large ZP extension, every prime different from P is sort of only splits a finite amount of time, and then you have a large sort of, and it's inert for most of the way. All right, so maybe that's. So that's our large Iwasawa Selmer group. And there's some brackets missing somewhere. So anyway. And so the question might be, so as we said before, if M gamma minus chi of gamma is W of chi inverse, one might ask, what is S? We have an action of lambda on X, on M, and that carries over then to an action of lambda on this Selmer group. And so we could ask, well, what's the what's this? And in particular, how does it relate to, I mean, the obvious guess would be that this would just be the Selmer group of E for maybe the character chi inverse. And so we want to see how much that's actually true. So I'm going to make a simplifying assumption for the moment, which is just going to be that E of P GQ is 0. So this is an assumption. Makes our life a lot easier. If we look at the multiplication, I'm just going to do this for the trivial character now, and you can sort of see the strategy. So I'm going to look at multiplication by gamma minus 1. M is we're taking the Pointeragan dual of lambda here with lambda star, so multiplication by gamma minus 1 is going to be surjective. It's going to be lambda divisible, and we've noted the kernel of that is just W. So we have an short exact sequence of GQ modules, and so if we just take the cohomology, right. So if we take the cohomology of this, we'll have a map from the fixed points of M into H1Q of W into H1Q of M, and then H1Q of M. This is multiplication by gamma minus 1. And so we can shorten this piece of this long exact cohomology sequence. The fact that the choice of this assumption we've made means that this is 0. This assumption means that that's going to vanish. And then what this is saying is that H1QW is identified then with the gamma minus 1 torsion in the large, this large group. All right. So does this work, or does it go backwards? That doesn't work. Oh, it does. Oh, good. All right. Fantastic. So now, then what we want to do is understand what the local conditions we've imposed on the large Selmer group mean for H1Q of W, the cohomology of W under this identification, and how do those relate to the conditions that defined the Selmer group of E in the first place. And I'll just show you, one small picture of that. Maybe I'll do the most complicated part. We'll do what's happening at P. So we've got H1Q of M of gamma minus 1, and we're mapping it to H1 of the inertia group of M, and it's gamma minus 1 torsion. And we have this identification of H1Q of W, and we map to H1 IP of W minus, and that's a surjection at that point by the same kind of short exact sequence becomes long exact sequence argument, but it is possibly a kernel. One thing to note is that we don't just land in the H1 IP of W, there's no W minus one, there's W. Or W minus, that was it. But there's an action of the local Gawa group on the whole cohomology. We land inside the part that's fixed by G of QP. This is the inflation restriction exact sequence. That's a minus. Oh, this is a minus too, thank you. And then there's an action of GQP here, which commutes with the gamma minus 1, so you can decide whether I wrote that over here or over there. There's a possible kernel here. What would the kernel be? We would have M minus fixed by inertia modulo the image under, the part to the left, so there'll be the gamma minus 1 of m minus fixed by inertia, and then the whole thing fixed by GQP. So then we have a short exact sequence like this. So our big Galois cohomology elements or Selmer conditions are telling me then that I'm looking at elements inside here that vanish here. If I'm coming from this part of the Selmer group, and so the only possibility of not vanishing in here is that you lie in the image of this part, and so now we want to understand what the image of that is. So the inertia group is actually acting trivially on W minus. How does it act on M minus? It's just acting through the canonical character. And so the fixed part of the inertia is exactly where gamma is acting trivially. So M minus of IP is just M minus where gamma is acting trivially, which was in fact just W minus. Gamma minus 1 is acting trivially on that, so multiplying by gamma minus 1 does nothing. So this is actually identified then with W minus of GQP. Now remember, the action of GQP on W minuses was by this unramified character whose value on a Frobenius was the unit root of the polynomial x squared minus apx plus p. So this is actually then just where the Frobenius is acting like alpha. And so maybe I shouldn't write it that way. What it is really where alpha p is equal to 1. So the whole point of this then is that this has order, the absolute or the order is the size of just zp modulo alpha p minus 1. Now, our condition for being in the Selmer group of W was not just that it was trivial under inertia, it was that we were trivial on the whole a local cohomology group. And so we also have to understand what's the image in H1 QP of W minus of things that vanish in H1 when we restrict to inertia, so the unramified part. And it turns out that by simple calculation it has exactly the same order. So I'll leave that as an exercise. Yes?
Why is M
M minus, the invariant of M. Oh, because we're assuming that the residual representation is 0, right? Has no invariance. And the residual representation is actually a submodule where P and gamma minus 1, where the maximal ideal of lambda is acting trivially. And then actually by a duality argument, that's a quotient, and then there's a Nakayama thing. Alpha P was so alpha P is the unit root of the characteristic of the polynomial x squared minus apx plus p. That was notation from the last lecture. I'm sorry I'm not putting all the notation back up. And just to clarify, E of P is isomorphic actually to M, where gamma is acting trivially and P is acting trivially. So then what in fact we have is that M of gamma minus 1P of G of QP, or not G of QP, G of Q is 0. That was our assumption. If we take, so the dual of this, one way to see what's going on is that then the dual of this is just the dual of M, which is some nice compact thing, modulo gamma minus 1P of M. And to say that there's no invariance is to say then that M dual has its invariants have a quotient by the maximal ideal that's 0, and therefore by Nakayama it's 0. It's in the notes. Um, oh, in the quotient, yeah. The other exercise is to fix all the mistakes that I make up here. So the upshot of this kind of analysis is that one has that the sum, again, under the assumption that, the simplifying assumption that this is 0, is that the Selmer group of E with even in any character is a subgroup, actually, of, so we have the Selmer group, and where we have to scratch that. All right. So we have E of P GQ 0. We have our big S. We might again have to extend scalars to O chi, and then we can look at the submodule where gamma is acting by the character chi. And inside here, we'll have the Selmer group of E for chi inverse, and this will be with turns out with finite index under the various hypotheses we've made, and we can even be more precise about what that index is. I'll only write this down in the case where chi is the trivial character. One has that you have the Selmer group of E inside S gamma minus 1, and you have the co-kernel. You have a product over all the primes that divide N of E. You actually have the unramified cohomology classes of QL of W. So the decoration at the bottom is a UR, meaning unramified. So it's the classes that vanish on restriction to the inertia groups. And it turns out that the order, there's something coming from P, which I haven't told you. And it turns out the order of this, though, is the P part of the Tamagawa factor C of L of E that was in the Burt-Swinnerton-Dyer conjecture, really the formula part of the Burt-Swinnerton-Dyer conjecture that I wrote down yesterday. And then there's this part that we've just analyzed. So there's something inside here from P, and this has order ZP of alpha P minus 1 as the square of that order. So order of that. Yeah. And so that's, in general, the co-kernel lands inside that. And in fact, if this, the Selmer group itself, is in fact finite, then this map is a surjection. So when the Selmer group of E, this is the P infinity Selmer group, is finite, that's really just the P primary part of the Tate-Schaffer-Ravitch group. So what we're seeing then is that this large Iwasawa Selmer group, we look at its gamma minus 1 torsion, then the order of that is the order of the Tate-Schaffer-Ravitch group, in this particular case, times the Tamagawa factors, or at least the P parts of the Tamagawa factors, plus a little bit of a correction at P. So that's looking very much like what one expects from the Burt-Swinnerton-Dyer formula. In fact, we've made the assumption that there's no P torsion, so there's no P part in the denominators for the formula to worry about either. And so, in fact, that suggests that the object that might be most closely related to the L value, LE1, normalized by the period, or at least its P part, would be this middle subgroup. So. All right, so at the very least, I hope I convinced you, partly by intimidation, that this large Selmer group S is packaging together the Selmer groups for this family of twists. Now, of course, you could consider other characters of gamma, characters that might have infinite order. They could still be nice geometric characters. You know, they could be a finite order character times the power of the cyclotomic character. So we would be taking Tate twists when we twist as well. And there, as I mentioned, there's sort of, you know, Selmer groups for such twists defined by Bloch and Kato. And you might ask, is there a relation between this large Iwasawa Selmer group and those? And the answer is it's not as close. And the thing is, which characters are sort of most closely related to one of these Iwasawa Selmer groups is dictated by the Pietic Hodge theory of the representation. It's a little bit delicate to go into, but it's in the notes as well. And so you can look at other twists and try to package them together, but what you would probably need to do, definitely would need to do, is change the local condition at the prime P for even the large Selmer group. And that's discussed in the notes. I don't know if I'll have time to go through it at any point in the lectures. But anyway, this Selmer group S is seeing these finite order twists. All right. One thing maybe we should note. What can we say about S? So we have S, and there's just some important things to note about it just as a module over lambda. So S is one of these cofinitely generated lambda modules. What does that mean? That means if I take X to be, and in my notes that's X e of Q infinity, to be the Pontryagin dual of S, S is a subgroup of a discrete module, so it's a discrete module. We take its Pontryagin dual, it's compact, and to say that it's cofinitely generated is, S is cofinitely generated is to say that X is finitely generated. So these are the equivalent statements. Just a quick, perhaps, explanation for why this is true. It's enough to show this for H1, what I was calling G sigma before. For some finite set of prime sigma, we take the Galois group of the maximal extension that was unramified away from sigma. We take sigma to be the set of primes dividing LP in infinity. That's going to act on M. And it's enough to show that this group is cofinitely generated. S is a subgroup, so its dual is a quotient. So if this group is if its dual is finitely generated, then X will be finitely generated. And to show that the dual is finitely generated, we just need to show by compactness that the dual modulo the maximal ideal is finitely generated. Well, the dual modulo of the maximal ideal is the dual of the kernel of multiplication by element, and things that are killed by the maximal ideal. So it becomes enough to show that this object is finite. And that's not so hard to see because we already saw that this is just H1 G sigma W. And so now we just need to show that H1 G sigma W is, well, the P torsion in that is G sigma, sorry, of W. We need to show that the P torsion in that is finite. And that's just H1 G sigma of the P torsion in W, which was E of P. And we're back to the same module that we looked at when we did the Wheaton-Delvaux theorem, and that's finite. So that tells us that this is a cofinitely generated lambda module. Over there. I'm not sure those are any help at all. But, so as we've heard, finitely generated lambda modules, like X, have a structure theorem over lambda. So X is pseudo-isomorphic to a product of cyclic lambda modules. The FIs could be 0, so there could be some rank there. And one can define then the characteristic ideal to be the ideal generated by these things. I'll call that, say, from I equals 1 to R. And inside X, if you like.
But not if some of them are 0.
Well, then it's just 0. Well. Happier?
Should be in lambda.
Oh, yes. Okay, I think I understand what I wrote. Good. And so then the question, sort of a natural question to ask is what does this characteristic ideal mean? Does it have any relation to the kinds of things we've looked at before? And so if X has no, and we've seen this, I'll just remind you, if X has no pseudo-null submodules, so if in fact, if we have sort of an injection of F then into such a product with some finite order co-kernel, then we can recover the image, the size of X modulo sort of say T, or gamma minus 1, from the characteristic ideal. So if you multiply by T, which is gamma minus 1, yes. I said if X is this torsion, yeah. That's yeah, right. I mean, so that's actually one of the parts of the problems is to determine when there's a free part and when there isn't when you're studying these modules. But suppose X is in fact torsion and has no pseudo-null submodule. You'll get an exact sequence like this. So multiply this by T, say, and now apply the snake lemma. And so you'll get from one part of the snake lemma, you'll get the kernel of multiplication by T on this finite order thing, which is certainly finite. So let's call this, what should we give? Let's give it a name, A. So we'd have AT into X mod T into the product of the lambda of FIs T, and then we would have then A mod T. And so so what's the kernel of multiplication by T here? That would be, the kernel of multiplication by T here, and that's 0 if 0 is not a 0 of any of the FIs. If FI 0 is not 0. So this becomes an injection if FI of 0 is not 0 for all these i's, for all these polynomials or power series. And then this is just isomorphic to Z mod Fi 0. And so you can see then that the order, well, since A was itself finite, these two orders are the same. And so that the order of the X mod T has to be the order of the product of these, that's a ZP, the product of these. So then we get that the order of X mod T of X is the order of ZP mod then the product of the FIs at 0. In fact, if you look at this argument a little more carefully, even if T was or did divide one of the FIs, so if FI was 0, then you would be able to conclude that X mod TX is infinite. So you can actually extend this with the understanding that if this side is infinite, then that side is infinite to an equality in general. And one should note that this could then is the same as the order of ZP mod, what I'll call G of 0 for any generator of the characteristic ideal. So this is just, all right. And so, and if you think about that, so what this is saying, so if x now, which is our x of e of q infinity, is lambda torsion and has no pseudo-null submodules, then what we have is that if by looking at this exact sequence, then we have that the order of x mod gamma minus 1 or of t of x, that's going to be the same as the order of s modulo, or the gamma minus 1 torsion in S by duality, and that we see is the order of the Selmer group of E times the Tamagawa factors, or the p parts of the Tamagawa factors, times this little bit of a correction term that came from the alpha p. So we have that squared. And again, this is what one expects from sort of just showing up in the Birdswin-Dyer formula. And this, on the other hand, should be the order of lambda modulo, well, gt, which was the order of zp modulo any generator at 0. And so what this is saying is that if the dual of the large Selmer group is lambda torsion has no pseudo-null submodules, then in fact we can see the order of the Selmer group times these Tamagawa factors plus this correction term at p as the value up to a p-adic unit, well, of the constant term of a generator of the characteristic ideal. Yes? That came from, so we now have an exact, this short, relatively short, exact, 4-term exact sequence. So we have an Euler characteristic, saying that the order of this times the order of this is the order of this times this. These two have the same order because A is finite. So if I take a finite order module and I have a homomorphism of it to itself, A was as this co-kernel of this map, of the inclusion of X inside these cyclic modules. There's a pseudo isomorphism, so there's a finite order co-kernel. So I'm just calling it A. And then we're multiplying that short exact sequence by T. That's a map between two short exact sequences, and now we're taking the snake, applying the snake lemma to that. Right now it's the dual of S. Yeah. If the Selmer group of V over Q infinity is finite, so it's finite order, then X is lambda torsion. You should be able to deduce that from what we've written so far. To say that X is lambda torsion, I just need to know that X, so here's the hint, I just need to know that X mod T of X has finite order. That's enough to tell you that X is in fact lambda torsion, and then you go back and look at the things that we've written down. This is a much harder exercise, so I'll use an exclamation mark. So this is finite. Then X has no pseudo-null submodule. Actually, you can say something much stronger. Just if X is lambda torsion, then it actually has no pseudo-null submodules. And so, in fact, everything we said on this slide applies. We have this. So I think I'm almost out of time. So let me just sort of say what I think we've done in the last 50 minutes, which is define an Iwasawa sort of module, a big Selmer group that packages together in some fairly precise sense the Selmer groups for finite order twists by cyclotomic characters of the Selmer group of the elliptic curve, and related the value of the generator of the characteristic ideal of that Selmer group, or of its dual, to the order of the Selmer group of the elliptic curve that we started out with. And in fact, as you can imagine, you can do this for all the twists as well. And so this gives us actually kind of the setup to which to start. We can, I guess tomorrow morning, formulate the main conjecture for elliptic curves, which is going to be trying to identify this a generator of this characteristic ideal as something that's actually related to L values. All right. I think I better stop there, right? So.
Questions?
So that big Selmer group, as it was defined in a bit unusual way, not as an inverse limit of something. Can it be? Is it an inverse limit of Sns over finite level?
Yes. So another way of defining Vs as in the big Selmer group S is that if we have this Q infinity over Q, right? We had there's some intermediate fields, say the Q sub n, right, with Galois group gamma of n. So this is Galois group Z mod p to the n, and S can also be defined as just the direct limit over the Selmer group, the cell P infinity, the usual Selmer groups for E, but now we replace Q by these QNs. And that's maybe how people might have seen this before. Is that what you're asking? Yeah, so here there's no, where does the twist by the character come? The twist by the character comes that as each one, because E is defined over Q, on each of these there's an action of the Galois group of Qn over Q. And that's giving me the lambda action. So that's giving me the lambda module structure. The equivalence with the definition that I gave before basically comes through Shapiro's lemma. So I can think of H1 of Qn of W, which is where these subgroups are defined, or these Selmer groups are subgroups of this. By Shapiro's lemma, I can think of that as H1 Q of the induction of W. But since W is a module defined over GQ, then you can relate this to W tensored with say the group algebra, or actually the homomorphisms from the group algebra into W, which is, and then as you take the direct limit over. I think this is also in the notes, at least briefly described. It requires a little looking at, but so yeah. So Selmer groups, Iwasawa Selmer groups are often treated this way. This would be much more analogous to sort of saying, well, we have a class group or a dual of a class group over each of these fields, and we're looking at how that module grows under like the norm maps. but I wanted to emphasize the sort of aspect of things where we're sort of packaging together twists, kind of a family of Selmer groups over Q. But they're actually equivalent definitions.
All right, why don't we have a break and reconvene at 3:40?